Okay, we can start. We can consider a very simple example. Y dot y dot t equal to minus 1 alpha y t. This linear differential equation in yt. We can write this equation as y dot t plus 1 half y t equal to 0. We can multiply both sides by e to the power 1 half t, which is the integrating factor. So we can write the first side as the derivative of yt e to the power 1 half t respect to time equal to 0. Now we can integrate both sides respect to time, which means that we can write this expression as yt e to the power 1 half t equal to a constant c, because the interval of 0 is a constant. This means that we can write the general solution of this differential equation as yt equal to the constant c times c to the power minus 1 half t. This is the general solution of our original differential equation. Now, in order to find the final solution, the particular solution, we can let's first step find the steady state solution of this expression. The steady state solution can be computed setting y dot t, which is the speed of our variable y, equal to 0, which means minus 1 half y star, which is the steady state solution right here, y star equal to 0. Okay, so the steady state solution is y star equal to 0. We can write the particular solution in terms of steady state solution. Now, we assume that the initial value at time 0 is equal to y0. This means that taking the general solution, y0 will be equal to c. So we can write the particular solution as yt equal to y0 times e to the power minus 1 half t. This is the particular solution. In this case, the, the steady state solution is 0. So this can be also written as y star plus y0, because y star is equal to 0. Now, if we want to check the stability of our steady state solution, we can, there are two ways. In particular, we can write again the general solution, the particular solution, which is yt equal to y star, which is 0, plus y0 e to the power minus 1 half t. We can compute the limit of t, which goes to plus infinite to yt. This is equal to 0, equal to y star. So this means that we can check that y star is globally stable, because also if the initial value y0 is other than 0, if time goes to infinite, which means that time go on, okay, goes on, finally y will converge towards y star. We can check this fact also computing in the differential equation the derivative of y dot respect to y. This is equal to minus 1 half, so it's negative. So if we draw the phase diagram of y dot respect to y, this is a decreasing function. Y star is the value at which y dot will be equal to 0. If we are here, the speed is negative, so we go towards y star. if we will be here, the speed will be positive, so we will go in this direction. Also, from this point of view, y star is globally stable. In our case, y star is the origin, is 0, so the correct picture is this. Okay, I will do in another paper. So in our case, y star is 0. So this is y dot, this is y, and this is our y star, which is globally stable because the speed is positive on the left and negative on the right. Okay, now we can try to do another example. For instance, y dot t equal to minus yt plus 2. This is linear in yt, but in this case we have also this term. We can write this differential equation as, so this is an example, plus yt equal to 2. The integrating factor in this case will be e to the power of t, because in this case we can write this first side of our equation as the derivative of yt e to the power of t respect to time equal to 2 times e to the power of t. So we can integrate both sides respect to time. This means that we get y of t e to the power of t equal to the integral of this is equal to 2 times e t plus a constant c. So we can get the general solution of our differential equation, which will be y of t equal to 2 plus c e to the power of minus t, which is the general solution of our differential equation. Now, in order to find the particular solution of our differential equation, we can first find the steady state solution, which means y dot t equal to 0. In the initial differential equation, we need to solve y star minus y star plus 2 equal to 0, which means that the steady state solution is y star equal to 2. Okay? This is the steady state solution. Now we can assume that the initial value at time 0 is, for instance, 0. Okay, we can give also a number as initial value. This means that taking the general solution, we will get that 0 equal to 2 plus c, which means c equal to minus 2. We can write the particular solution as y of t equal to 2 plus c, which is minus 2, so it's minus 2 e to the power of minus t, which is equal to y star. Okay, we can write also this way, plus 0 minus 2 e to the power of minus t, which is y0 minus y star. Now, this is a particular solution. We can write also in this way, y star minus 2 e to the power of minus t. This is a particular solution if we assume that t is equal to 0. Okay? Now we can check the stability of this steady state solution, computing the limit for t which goes to plus infinite of yt. This will be equal to, if yt is equal to this, will be equal to y star. So this means that y star is globally stable. If we want to check to the phase diagram, we need to compute in the initial differential equation b of y dot respect to y, which is equal to minus 2, so it's negative. This means that the phase diagram of y dot respect to y is decreasing. This is 2, our steady state solution. Here the speed is positive, here the speed is negative. This means that the steady state solution 2 is globally stable. Now we can solve another linear differential equation, for instance y dot t equal to 2t yt plus t. This is also a linear differential equation, but in this case uh, here we have not a parameter but a function of time, and also here, but the methodology is the same. So we can write this as y dot t minus 2t yt equal to t. In this case, the integrating factor would be e to the power of minus t square, e to the power of minus t square. Why? Because in this way we can write the first side of this equation as the derivative of y, the derivative of y of t, which multiply e to the power minus t square respect to time, and here t e to the power minus t square. Now we can integrate both sides as usual respect to time. This means that we can solve this integral, and we get we yt e to the power minus t square equal to the integral of t times e to the power minus t square will be equal to minus 1 half e to the power minus t square plus a constant c. So the general solution of our differential equation will be yt equal to minus 1 half plus c e to the power of t square. This will be the general solution of our differential equation. Now, in order to find the steady state particular solution, we can start solving for finding the steady state solution of the differential equation. We need to set the speed of particle y equal to 0. This means that 2t y star plus t is equal to 0. So we can get steady state solution y star is equal to minus 1 half. Minus 1 half. In order to check the speed, we first find the particular solution. We can use an operator. Particular solution, we can set the initial value of time 0 as y0. This means that for the general solution, y0 is equal to what? Is equal to general solution minus 1 half plus c, which means that c is equal to y0 plus 1 half, which is equal to y0 minus y star, because y star is minus 1 half. So we can write the particular solution of our differential equation as yt equal to y star, which is minus 1 half, plus c, which is y0 minus 1 star, e to the power of minus of t square. This is the particular solution of our differential equation. If we compute the limit for t which goes to plus infinite of yt, this will be equal to plus infinite. So from this perspective, y star is globally unstable. We can check the same if we compute the derivative of y dot respect to y in the initial differential equation. This will be equal to 2t, which is positive. So in this sense, if we consider the phase diagram, we know that the steady state solution is minus 1 half, but the derivative is positive. This means that this function is increasing in y in the phase diagram. So if we are on the right we go in this direction because the speed is positive. If we are on the left, we go in this direction because the speed is negative. Also, in this perspective, the steady state solution y star equal to 1/2 is globally unstable.